Start it out. Good afternoon, everyone. Thank you for being here. Thank you for the invitation and for the introduction. So yeah, I'm Reetam. I am a postdoc at the Southeast CASC. And over the last couple of years, I've done a bunch of fire-related research, mostly with my PIs. Adam, who is, I think, in the audience, and it's his slides that I've heavily cannibalized. So the moment I, have any questions that I can't answer, I'm going to throw that to him. But also heavily with Brian, who is in the Department of Stats, and like me, we both have stats backgrounds. And the majority of this research has been fairly stats heavy, but given the audience today, I wanted to focus less on the statistical aspect of things and more on the actionable aspect of thing, and also the ecological aspect of things. So I usually don't do tables of contents, but I think in the context of this talk, it would be helpful. So maybe the first 40% of the talk is just going to be background. This is the bit that's cannibalized from Adam's old slides. Just laying some groundwork on what motivated my research and where it goes next. When I talk about the recommendation engine, which is a statistical tool, I will very briefly go over the stats of it. No equations, just vibes on what it is and how it helps us. And focus more on the results for our case study, which is for the Eglin Air Force Base in Florida. And we're going to wrap up with both some specific questions about the tool and some broader questions about the research that I have been doing. So a lot of this was motivated by a paper. There are two papers here. The one on the left is the one I want to point your attention to. That was written by a bunch of my PIs, Adam and Kevin, also John, which looked at prescribed burning windows in the Southeast, fundamentally looking at how many days are viable for burning every year, given current weather conditions and potential future weather conditions, and looked at how that's going to change both in the short term and also in the long term until the end of the century. And of course, the title is a spoiler alert there. And I will also be going over a specific slide from this later on. This was one of the things that they kind of looked at. And the reason for the focus on the Southeast is because prescribed fire is a critical management tool in the Southeast US. The Southeast has the largest, I think, amount of area burned in the CONUS every year compared to the remaining parts of the country. It's a very important management tool. It has two primary goals. The first one that I will not be talking about because it's not my expertise at all is habitat management, but it is super important. The one that I will be focusing more on is wildfire risk reduction. So I have a couple of slides, which if you look at the dates on the x-axis, you'll realize they are literally a decade old because they form the basis of the paper I mentioned in my initial slide. This one, both are from Georgia. This one shows that the amount of prescribed fire has gone up over the 2 decades that it presents. And correspondingly, the number of wildfires over that period of time also kind of went down. So prescribed burning, at least in the Southeast, did lead to a fair amount of wildfire risk reduction. It's fairly well studied and documented. We've seen similar patterns when I looked at the Eglin Air Force data when I worked on it. But unfortunately, the amount of burning that can be done is sensitive to climate change and climate variability, and in many cases is kind of stagnated. Because if you look at this plot, which shows both the number of burn permits every year, which is in yellow, and in red, the amount that was actually burned over this period in Georgia, you'll see that the number of burn permits hasn't really changed much, but the amount of burning that was done either stayed the same or actually went down. And of course, there are a bunch of reasons for this, but one of the reasons is kind of what was alluded to in that initial paper, that prescribed burning opportunities are going down because climate is changing and there are fewer and fewer days that are available to meet these prescribed burning objectives. And so the overall question for that paper that Kevin and Adam and John wrote was that how could projected changes in climate affect these prescribed burning opportunities in the Southeast? Will they remain constant? Will they change? How will they change? And the criteria that they used for kind of classifying days and periods as can you burn on this day and can you not burn on this day was mostly meteorological. And they didn't come up with this, but they validated these on, I think, thousands of burn plans and also previous research. Three of the most important variables that they looked at were temperature, relative humidity, and wind speed. Their importance to prescribe burning is, for the most part, self-evident. Can't be freezing, can't be too hot, cannot be too dry. And also, wind needs to be at this Goldilocks zone so you could actually do prescribed burning. These are obviously not the only variables of interest. And in my work, I have additionally, for example, looked at precipitation, but these are definitely necessary variables that we need to look at when figuring out whether prescribed burning is viable on a particular day. This is the big picture result that they had, where each row corresponds to a time period. So this historical and the two RCPs that you see mentioned, for those unfamiliar, were based on CMIP5 climate projections, which was the last generation of this. And the two versions, 4.5 and 8.5, 4.5 was the optimistic sort of climate pathway where, carbon emissions are brought under control. 8.5, I have seen referred to colloquially as business as usual. And what you see on all the maps, which are also segregated by the seasons, is the proportion of days that are what we'll call within burn window. I will also use the phrases, within prescription, viable for burning. It's the same idea. Like, can you burn on this day? Will the meteorological conditions allow you to burn on this day without it, A, becoming a wildfire, or B, just, not being able to burn because it's too cold or too rainy? And overall, unsurprisingly, they found that in the summer, the percentage of days that are viable for burning are going down. That's the wildfire risk aspect of it. The transition period months that you have in the middle, they also went down. The winter period was the least affected because obviously temperatures stay in control, but obviously in the winter period, there are other issues if you try to do prescribed burning. And so based on this, the follow-up question from the research from back then was, can burn managers adapt to this changing climate in a way that allows them to accomplish their short-term, medium-term, and long-term objectives? And this was the basis of the proposal that I was funded through, that I have been working on for the last couple of years. In particularly, the work I want to present today focuses on the short-term aspect of that research question. So looking at how climate is changing and given immediate weather conditions, and the idea that there are fewer days that might be available for burning, what's the best way that we can help burn managers accomplish their short-term objectives, which generally speaking is burn whatever you want, or they have to burn within a fixed period of time within that season. And out of that research came out this recommendation engine. Is like fancy phrase, but it's fundamentally a statistical tool which has two components. The first one is what we call a fail state estimation model. I've already kind of laid the groundwork of what fail states are, but I will explicitly define it a few slides down the line. And the second part is, given the understanding of fail states, which is just quantifying whether or not you can burn, given that information, how do you select the best plots to burn so that fire managers can go about it in an efficient fashion? The overall formal goal was that given weather conditions, which is critical for the decision making, and information on burn plots, because you need to know how many plots are there that need to be burned, what are their areas, where are they located, a bunch of information about them. We wanted to kind of give a metric, which is like a parcel benefit for burning any of these burn plots. You can think of it like a score. for each parcel. It's like higher the score, the better it is for burning. It could be better because it's a larger area, or it could be better because, for example, the weather conditions are very good and we should get this burnt as soon as possible. And then once you have scores for every parcel over a 3-day burn window, which is our definition of short term, which comes from the fact that weather forecasts, there are 3 data products. The shortest one have 3-day forecasts. So for example, today, tomorrow, day after. And then there's a medium term up to 7 days, and there's a long term. So the shortest one being the 3-day window, identifying, okay, over the next 3 days, assuming I can burn maybe these many plots total, this much area total, what are the best plots to burn? How can I maximize the amount of burning that can be done, given whatever constraints that burn managers might have? And the end goal being that it gives them nuanced information that helps the decision-making process by providing options with the highest likelihood of success. So choose plots in a way such that weather conditions are most likely to hold over the next couple of days. So they don't change suddenly and you're unable to burn, or they're not so close to the burn thresholds that you're instigating a high amount of risk if you choose them for burning. So kind of make it safe and give them the best options. Coming back to the slide I had earlier, the criteria for burning, this temperature, and I'll separate the temperature out into a maximum and a minimum temperature, because if it's freezing, can't really burn. If it's really hot, too risky. So there's temperature, humidity, and wind speed. And I'll also have precipitation on top of this. And then the simplest definition of a failed state is the probability that these burn criteria are not met. And again, as I mentioned a couple of slides earlier, depending on which of these criteria are not met, the definition of a failure can be very different if they end up burning. You might not be able to burn, or it could become a wildfire. And there's a myriad of possibilities in between. So now more formally, how does the failed state estimation work, and how does this help over existing methodology and existing products that managers have access to? So the input for this part of the statistical tool, which is at this point, a model that has already been trained, is the 3-day weather forecasts. So we get them from the National Weather Service. More formally, the database is known as the NDFT. It's very easily accessible to anyone, and the data is fairly extensive for the continental US, though it doesn't go back too far. I think it goes back roughly a decade, and then it's a bit spotty. The output is calibrated forecasts with uncertainty estimates, and I'll go into detail about what both those phrases mean. The model itself is what we call a Bayesian hierarchical model, and I think this is as much stats that I'm presenting today. But the idea is that it will jointly estimate Tmax, Tmin, which is temperature, relative humidity, and wind speed, and precipitation. Now, there are some upsides to using a Bayesian approach, which is its own field of study within statistics. You get uncertainty estimates with basically any Bayesian model. If you look at regular weather forecasts, they will often just give you a point number. Like, 2 days from now, maximum temperature is going to be 80. It's 80 here because I wrote these slides, I think a few weeks back when, temperatures were a bit more reasonable. They just give you a number, but of course, 2 days from now, it's not going to be exactly 80. It's going to be in a ballpark of values that you will not know until the actual date, until the time has passed. But to make that decision, it's helpful to know what range and how certain we can be beforehand of that number. So we can have an uncertainty estimate like, the 2-day forecast from the weather service is 80, but once we throw it into the model, it spits out a calibrated number, which is like fancy for it's more accurate, that it's going to be in a range of say 78 to 82.5 with a 95% probability. So high chance that it's going to be within that range. And that's what we kind of mean by an uncertainty estimate. You get a range, and so you have more information on the actual number, and you also get a sense of how reliable is that number we're giving you. And the second part of the model that we have is what is called a joint model, in the sense that it takes into consideration the fact that the 5 variables that we're working with are correlated with each other. If humidity changes, the probability of precipitation also changes. Things like that. They don't exist in isolation. They're all part of the underlying same physical processes. And so it takes into that. So when it gives out these numbers, when it gives out these forecasts, they respect the fact that all of them have uncertainties associated with them, and they do that as a sum total instead of dealing with them individually. So how those sort of uncertainty estimates translate to failed state estimation is through just modifying the sort of statements we can give. So alongside statements like, hey, the 2-day forecast from the Weather Service is 80, and if I use the failed state estimation model, we can say that there's a 95% probability of being 78 to 82.5. You can rephrase that, or the model will give you the same sort of information in a different fashion that is more usable, where it will say, hey, the 2-day forecast is 80, but there's a 99% chance or probability that the Tmax will be less than 90.5, which was, the criteria for the threshold for prescribed burns. So it will directly translate it to what does it mean in the context of the numbers I care about. Because if it goes above that number, we can't burn. But we are 99% sure that it's going to be below that 90-degree threshold that we have. And so it immediately gives you an understanding. It's very likely temperature is going to be within threshold. But also that's not itself sufficient. We also wanted to say, what's the probability that, how likely is it that all the 4 or 5 variables are going to be within threshold? The Bayesian model can also put a number to that. It'll also give you ranges like I showed earlier. So if a burn manager wants ranges, those are there. But if you just want, a likelihood, how safe is this day for burning, or how safe is this plot for burning, you can get a number to that. And that is fundamentally a burn viability score, or a parcel benefit of burning a particular parcel. The higher the probability, the safer it is to burn on that particular day. And we can get this number based on both the 1-day, 2-day, and 3-day forecasts. So we have information for a 3-day window at any given time point. Now, what other things are important when it comes to figuring out which parcels might be the best to burn? The obvious baseline was it has to be viable given the weather, but also given that it's viable, what are the other discriminating factors? The 2 obvious ones that we have in our tool currently is the area of the parcel, where larger area better for burning usually, and years since last burn. I'll go into years since last burn in a bit more detail in the next slide. But in these 2 plots that I have, one for each of the variables, you'll notice that the y-axis is always 1. And keeping everything between 0 and 1, days and the probabilities, just helps with interpretation. Where the idea is that the highest utility you can get from burning any parcel is 1, the lowest is 0. And, like burning a parcel of, say, 10 square kilometers, much better than burning a parcel of 2 square kilometers, according to the way we have it set up. But beyond that, there's maybe not a lot of additional utility if it's too large, because maybe other costs come into play, like, actual cost, manpower, other logistics, that sort of thing. But these are just placeholder functions we're using. When operationalized, burn managers will be able to provide their own utility functions. So the area one I'm hoping is fairly enough to interpret. The year since burn, all I will bring your attention to is the shape. It's like the utility initially increases after maybe the first year, then there's a Goldilocks zone, and then it falls down. And this was done after discussions with several managers, but this is not the only type of utility function that can exist for years since burn. It was just what was most appropriate for our case study. And in general, the year since burn kind of aggregates a bunch of things. It aggregates habitat, condition, and quality. So for example, if it's been too long and you haven't burned, maybe there are mechanical treatments that are needed before you can burn again. So it kind of takes that into account. Wildfire risk, there's a point there where if you burn, then there's a highest risk of wildfire. It kind of takes that into account. And also efficacy and efficiency, where, in this Goldilocks zone is probably where burn managers want to, that's the frequency with the burn managers want to burn. And that's going to be different for different regions, but this was what we had for the Eglin Air Force Base. So this sort of general shape is what we chose for year since burn. We could also build in additional utility functions, which could include area, which we have, maybe distance to the wildland urban interface, where, burning a location that's very close to the WUI carries more risk, or maybe distance to nearby tracks, where if there are a bunch of parcels which are very close to each other, maybe we want to burn them as a group together because it's logistically simpler, as opposed to burning two different parcels in two different parts, of the area, which will maybe then require two different teams. So some of these are already built in, some of them can be built in very easily. You can just think of modules that can be plugged in. And once we have that information, we switch over to figuring out then, okay, which are the best parcels to burn, given all of this information. I will say ignore the plot on the right for the time being. It's like a teaser image, which I will explain maybe like 7 slides down the line. But more importantly, let me go over how the algorithm actually works. The idea is that once we have the list of burn tracks with their locations, their area, and also year since burn, the locations help us figure out what's the weather conditions going to be like. And we also need the weather forecast for the region, which we will then calibrate. Step 1, we assess the probability of a fail state at each burn plot. Step 2, we determine the utility functions for each burn plot, essentially these two pieces of information. And then we provide an output, which is two things, which has a probability of staying within prescription. It's a number between 0 and 1. Higher number means it's, safer to burn on those days. And we also provide an expected utility, a global utility of burning at that location, which I'll demonstrate in the next slide. And then based on that, it's very simple it's not simple, but it's straightforward to find a ranked list of locations. Think of it as a portfolio, which maximizes that global utility given the constraints that we have put in there, as well as additional constraints fire managers can add. Okay, I think this slide and the next slide have the most numbers, but I think it's kind of necessary to get the idea through of how the allocation happens. So this is a very simple toy example. Say you have 3 locations, 3 burn plots that need to be burnt over the next 3 days. Further assumptions, just for simplicity, you can burn exactly 1 burn plot a day. This can be relaxed. And step 1 would be computing all the things that I mentioned here, the probabilities and the utilities. So for a single plot, its area doesn't change. Let's say it's large enough that the utility from area is always 1. The threshold probability is going to be different on the next 3 days. Think, for example, Friday, Saturday, Sunday. Sunday is the safest to burn this plot, and Saturday is the least safe. The year since burn is actually going to be the same to maybe like 3 decimal places over a 3-day window because it changes very slowly. But for demonstration purposes, I just changed their number slightly. And then the overall utility is just going to be a product of these 3. There can be other metrics for the more quantitatively minded in the audience. It could be like a weighted average. The manager can decide which one should have a higher bearing towards the global utility. But in the simplest case, give them all equal weightage. So a product or a sum gives you a global utility. Now, say we do this similarly for the remaining 2 plots. And then we end up with a table like this. 3 plots and a global utility value for each of the 3 days. So like these 3 have now become this plot 1, day 1, plot 1, day 2, plot 3, day 3. And so the question then is, which plot do we want to run on which day? Like plot 1 on day 1, plot 2 on day 3, plot 3 on day 2. What's the best combination that will have the maximum, total utility? Mathematically, that translates to which combination of 3 values do we need to choose one from each row, because you can't burn a plot more than once. So if you burn a plot, say on day 1, it's no longer available on day 2, for example. So which combination of values, one from each row, should you choose such that the sum is the largest? That's the mathematical problem. And that's what the allocation algorithm solves. There are several wrong answers to this question. The simplest answer that you can think of, which feels intuitive in some ways, is like, hey, I'll look at which plot is the safest to burn on Friday, or has the highest utility on Friday. I'll choose that. Well, now that's immediately out of the picture. On Saturday, amongst the remaining 2 plots, I'll choose the one with the highest utility. And on Sunday, there's just one left. I'll choose that one. And if you do that, this is going to be your total that you can get. This is almost always not the best option. There do exist multiple algorithms which can, solve this problem. It's a mathematical problem with a unique solution. The name for that is something called the Hungarian algorithm, and not something I did. There's code for this. I just plugged in this matrix and it gave me the solution, where incidentally, the way I had it set up is if you burn plot 1 on day 1, plot 2 on day 3, and plot 2 on day 2 and plot 3 on day 3, it will have the highest total. Like you choose any other combination, it's going to be smaller than this number. And that's what the allocation algorithm does. There are a couple of other considerations here. So for example, if you remember, I mentioned the threshold probability early on. What happens if the burn manager decides I am not going to burn unless I'm at least 90% sure that the plots are going to be within threshold? It's a very valid situation. And as we'll see in the case study, like they might not be making this decision in their head very formally, or they might not be thinking of it as a 90%, but they're definitely making these decisions using their expert knowledge, just in a more informal way. So if you decide that, or if a burn manager decides they're not going to be burning unless there is at most a 10% chance of a failed state, that immediately takes out, for example, for plot 1, the 2-day out of the question, because this is less than 90%. And so what the allocation algorithm will do, it will just not consider this number when it's kind of choosing what to burn when. Again, it's automatically taken care of. In our example, it's not affected because we don't try to burn plot 1 on day 2. Plot 1 is already burnt on day 1. But it does affect in a lot of plots on a lot of days. And the simplest kind of outcome of that is there are long stretches of the year where there is no plot which is viable for burning because the threshold probability is always too risky to burn. The other thing to mention here that this keeps rolling on, this allocations keep happening over 3-day windows. So today I decide what I'm going to burn Friday, Saturday, Sunday. On Friday, I get another set of 3-day forecasts, which includes Saturday, Sunday, and also Monday. And I revisit the decisions I made, make sure everything holds up, make sure that suddenly nothing has gone outside of prescription, make sure something hasn't severely changed. And on a rolling basis, fire managers can keep making these decisions. There are obviously other nuanced criteria that the tool considers, both explicitly and implicitly, which I haven't presented. Like, for example, what happens if plot 2 that I chose for Saturday is suddenly out of prescription based on tomorrow's forecast? How do I work around that? That's kind of built in. Or things like, burning multiple plots in a day is built in. Constraints on this is the maximum amount of area I'm allowed to burn in a day is built in. And there are things that are not built in that can be built in. Now we move on to the last part, which is the case study. And before that, I'm going to take a breather. If there are any immediate questions, I'm happy to answer them. Otherwise, I want to continue on.
Yeah, Reetam, we've got 2 in the Q&A box here. Let me pull them open. Thomas asks, have you looked into including minimum mixing height to number of available burn days? One of the lesser discussed issues nationally is that we don't have a standardized way of calculating mixing heights.
Sure. And okay, I see that, and I see the next question as well. So I'll answer
Great.
both. Very
Thanks.
quick answer. For Thomas, we looked at mixing height. It was hard to work with because it's not a product that's available in the weather forecasts directly. And so being able to kind of work with that was a bit tricky. Also because we would have to work with wind direction, which is again hard to model a bit statistically. So those like wind direction and things like mixing height and vapor pressure deficit are things we want to look at in the next phase. To answer the other question about the availability, this is currently not on GitHub yet, but I think sometime later this year it will be. It's not hard to implement. The code is very straightforward, very off the shelf, and I'll talk about that near the in my last few slides about operationalizing this. Okay, so moving on for the case study itself, we chose the Eglin Air Force Base because there was a bunch of data available. It's in Florida. We have data since the 70s, including very detailed information of every fire that has happened in the 70s. Well, not every, but most of them are documented. So, the start and end dates. For prescribed burns, when was the time that they were last burned, which gives us years since burn information, as well as like geographical areas of every single burn. And we have the 3-day weather forecast data from the National Weather Service. The observational data came from something called GridMet, which is, again, openly available. It's a great standard use data sets, and we'll also be using this when we do the long-term version of this. And as I mentioned, the weather forecast data is a bit finicky before 2015. They're different resolutions and a bit spotty coverage, so we use 6 years of data to fit our model, and then validations to kind of check whether the allocations the model gives makes sense in terms of what actually they did, and also from a physical perspective, or whether they're completely unhinged from reality. So we use 2021 data to kind of do that. This slide is here just for completeness to show that, when we fit the model and we look at those predictions, these are the calibrated values. The forecast is the calibrated. And generally what we found that they are much closer to the observed values than the 2-day and 3-day forecasts from the weather service used to be. So we were able to improve on them. And we were also able to provide uncertainty bounds around them, like what values are they likely to be within. Now, to come for the actual allocation part, which is the fun bit. This slide is half empty because there are 2 more panels in the next couple of slides. So what you see on this slide on the right is there were 56 plots that were burnt in Eglin in 2021. And those are the ones that are plotted here. These are their actual burn dates. The colors represent the size of each plot. I forget the unit. This is not in square kilometers. I think this is in acres. But darker colors, larger plots. And also this represents, the y-axis represents the year since last burn, where the longest one was a 16-year-old plot, and the shortest was stuff that had been burned within the last 1 or 2 years. And this was how they were allocated. You'll notice that a lot of the larger plots are burnt initially, and a lot of the smaller plots are burnt later in the year. This is the summer, where you can't really burn anything because nothing is viable for burning. This is the allocations that our model provided for 2021. If you remember, I talked about the threshold. So this is 90% threshold, which means that the burn manager is more or less risk averse, that unless they're very certain that it's safe to burn, they will not burn. This is a more risk tolerant approach, that as long as you're 80% sure you can burn, you will burn. And unsurprisingly, if you take the risk-averse approach, there are plots that you can't burn in the beginning of the year that gets pushed back to the end of the year. However, if you're willing to be a bit more risk-tolerant, you can burn a lot of these plots early in the year. Especially if you notice the super top one, this is the 16-year one. The utility is super low because you haven't really burned it in 16 years. So by default, it'll end here. But if you're willing to be more risk-tolerant, you can end up burning this fairly early in the year. And you will notice that this 90% one is the one that's relatively close to what happened in reality. And in particular, if I plot the left panel and the right panel and the dates of each of them, there is a fair bit of agreement. Sure, our model has more late year burns just because of that, the threshold we put, which was kind of arbitrary. So if we tinker that around, I'm pretty sure we can come to something that's very similar to what happened in reality. But by and large, the time period where we say is the best time to burn is usually the best time to burn. with just more nuanced information. I will very briefly go over 3 specific plots. The first one is year since burn 7. So it's the part of that curve where it was starting to fall. And this is for a single plot. This on the right-hand side, it shows that probability of it being within threshold. And as you can see, like if you want it to be above 90%, there are very few days where you can burn, just whatever is above like this line here. For large parts of the year, it's not within threshold. And this is their actual utility, which just multiplies the threshold probability with like area and years since burn. The circle is when it was actually burned. And the threshold probability on that day is very low because if you notice, on the actual date it was burned, the humidity is less than 30%, which is the standard cutoff we were using. Interestingly, the forecast for this day said humidity was going to be above 30%. So when the decision was made, they were working off of incomplete information, but they made the best decision with the information they had. But that's why this probability, once you know this, is below what would be the threshold. The day that the model suggests for burning has a much higher probability. Everything is well below threshold, and it can allocate it much earlier. And so we are able to give this sort of nuance. We will usually know that if the forecast is say 31, relative humidity 31%, what's the range of values that is realistically going to be? This one had a year since burn of 2 years, so it's in the rising part of that curve. I'm going to show that curve again. I should have had it later on. Year since burn 2 is in this sharply rising part of that curve, which means that by the time, when you multiply that, later on has higher utility. Similarly, the threshold probability always looks very similar because that's just standard weather stuff. It's the same for most locations. In reality, this was chosen to be burnt near the end of the year, again, around conditions that were very close to the threshold. But if the algorithm is used and you allocate based on that, it's possible to find days beforehand. And the third one is that plot that I mentioned, 16 years. They burned it like that was the first plot they burned that year, even though it was technically below freezing that day. Probably because if it's freezing, it's still less risk than a risk of a wildfire. You can still burn it. If it doesn't burn, just try later. But if you treat that risk, same with the wildfire risk, and run the model, do the allocations, because its utility is so low and it hasn't been burned for so long, it will show up at the end of the year. That said, there are things that are not taken into consideration here. Like, for example, maybe for plots like this, which haven't been burned for so long, fire managers are more risk tolerant because they just want this to be done with. There probably are considerations around area and manpower and logistics that are not built into here. But once a fire manager is given, say, like a portfolio like this, they can make further decisions based on this. Okay, this is what the numbers tell me, but this one is not viable because of practical reasons, and carry on with their best judgment. Which brings me to how this is being implemented in our case study for the Eglin. Now, what's next for this, which will answer some questions that have been asked and probably some that will again be asked. If you remember this thing I had earlier, the opportunities to burn will be affected as time passes. So it's immediate, it's of immediate concern to maybe think about, should we be relaxing those fail state constraints in special scenarios, like locations that haven't been burned for very long and it doesn't have a risk of a wildfire. The model can very easily accommodate that. Just the probability of it being within threshold will change, nothing else. We want to expand the set of utility functions. So we conducted a workshop last December with Jaime, one of my PIs, and his student Emily, who I think is in the audience. There was a workshop with 5 practitioners from North Carolina, which helped us get additional constraints like cost and manpower, which obviously we don't explicitly have in our model, but can be built in, and which will also differ from management scenario to management scenario. And the second thing is, custom utility functions, which will again vary based on stakeholders and the sort of flora and fauna, the habitat management aspect of it. Some of it we will incorporate, but the upside is that, some of it can be incorporated by fire managers themselves when they try to use this. The next big thing we care about, obviously, is making this medium term and long term. So things like opportunity loss can be formally quantified. So things like, hey, if I don't burn this plot this week, will I have another opportunity later in the year, maybe in the winter? If I can't, what's the downside? Will I get an opportunity to burn next year, or will it go out of prescription next year? And I might need to do mechanical treatment. So the opportunity loss, which is the flip side of the risk of burning, we want to incorporate that more formally, and it'll also help make more nuanced decisions. And finally, what I think is the most important piece is operationalizing this tool. As I mentioned, the methodology is off the shelf. Anybody who installs R, which is a statistical programming language, can run the code, run it for data for their part of the country. This is pre-trained, so this will probably work for several parts of the US, specifically the Southeast anyway. All they need to retrain it for their region, if they want to, is that weather forecast data from the Weather Service, as well as observational data. Both of these are very easily available for the Southeast US. And of course, different parts of the country, even different parts of the Southeast will, require additional constraint, additional utility functions. They can use ours, or they can supply their own or modify ours. All of these are options that are very easily implemented in the model. And yeah, and with that, I would like to conclude. Thank you for your attention. Happy to take any questions, comments that might be there.
Thanks so much, Reetam. You just answered one question. So Delana, you'll see that I put yours into the answered side. But we do have two questions in the Q&A, and I'll invite folks, if you have others, please feel free to click on that Q&A box and type them into the box. Maddie asks, do you take smoke dispersal into account in your model? Minimum mixing height is important for smoke dispersal.
Yeah, I vaguely alluded to this when I mentioned the wildland urban interface, because that's one of the things I know is super important in the Southeast. But because we don't have the wind direction and the mixing height piece, we have not been able to do that yet. That said, I'll mention this, like, this tool doesn't exist in isolation, right? It will give you a set of recommendations, but if our managers already have their own ideas on smoke dispersion, they have it from, for example, a different numerical model, you can use that in tandem with this. Like, in this list, which are the safest ones when you take smoke dispersal into account? And that works. But ideally, yes, ideally we want smoke dispersal to be part of the model itself.
Thanks, Rita. And then Nicholas asks us, I think you kind of covered this, but maybe you could be explicit about it. What is the spatial scale of the input data? And is that the same as the scale of the predictions? For example, if you have different input meteorological data, does that then dictate the scale of your predictions?
That is a great question, which is kind of swept under the rug, which I will go back here. So the National Weather Service data, if I remember right, comes at 2.5 kilometers. The GridMet data, which is, or actually maybe it's the other way around. One of these is 2.5 kilometers, one of these is 4 kilometers. Maybe the national weather data is 4 kilometers. So what I did in my study was I put everything into the same spatial dimension as the National Weather Service data, because that's what managers will have access to. And they don't want to have to deal with, all the transformation. And so, like, even though I think the GridMet data was available at a high resolution, I averaged over that to get the NDFD resolution, so that, you get NDFD resolution in, you get NDFD resolution out, but just with more accurate values.
Thanks, Reetam. Yeah, we had clarification here in the Q&A that GridMet is at 4 kilometers.
Okay, there you go. So yeah, I put everything in the NDFD scale.
Great. Mike is curious. Oh, this is a question for me. Mike, I will put it on YouTube and I will put it on the website and I can send it to you as well. So I will send the recording your way too. But if you search for this webinar title anywhere in the next, give me about 3 hours, you'll be able to find the recording for it. And then Ryan, how sensitive is the model to training data? The National Weather Service Digital Forecast Database goes back to 2004, so wondering if more data would help improve, or does the model reach similar skill with fewer, more recent forecasts?
Yeah, so the NDFT data does go back to the previous time period. I'm trying to remember why I didn't go back between 2015. One thing I absolutely remember was before 2015, the resolution was slightly different. And I just did not want to work with resolving two different resolutions of data. But in general, for the continuous variables, we are pretty good. But probably if we have more information on the precip information. So there are two variables in particular. There's a probability of precipitation that they provide and a precipitation amount, a quantitative precipitation forecast that they provide. Those, obviously, more data is helpful because they are trickier to estimate, which brings me to one upside of the model itself, which I mentioned in the second point in this last slide, is Bayesian models can be updated to incorporate new information. So even if for some reason we cannot go back, as of today, as of 2024, I can technically take that same model, hammer on the 2021, 2022, 2023 information onto that without having to start from scratch, just update it and do predictions for 2024. So you can improve skill that way by cumulatively building upon the quality of the model, which I think makes more sense than arbitrarily going back as well, because we care about what's happening now and what will happen in the future. So the latest information is always, I think, more realistic to the sort of predictions we want to give.
Mm-hmm. Yeah, thanks, Rita. And Adam has a similar-ish answer here in the Q&A as well to talk about the steps that this tool will have going forward. So with that, Reetam, I'm going to go ahead. I'm going to share my screen. I'm going to kick yours off. Reetam, thank you again for this talk.
Yeah, thanks for
I'm not
having
joking.
me.
It's been since January. I've been telling Reetam. So thank you so much. I really appreciate learning more about the work that you've been able to do during postdoc, and best wishes onto where you're moving next. Do you want to
Yeah, sure.
launch that?
As I think Adam has maybe already put in the chat, I am joining the University of Arkansas as an assistant professor in the fall in the mathematical sciences department. I intend to continue doing a bunch of phi research going forward, both in the statistical side of things and more in the application side of things. So I hope there will be updated versions of these in the near future.
Brilliant. Thanks, Rita. And yeah, hard launch on the next thing coming up. So appreciate it, everybody. Appreciate y'all. Normally, this is the time and the webinar where I tell you what the next talk is going to be, but we are taking a break for July. We'll be back with the webinar series in August. So I'll encourage you to go ahead and subscribe to the newsletter if you haven't already. That's where we post all upcoming seminars, jobs, funding opportunities, news, everything else comes out once a month in that webinar. So with that, Reetam, again, thank you very much. And everybody else, have a great day.